Okay, let me get rid of this and then start to talk. Okay, let's get started. First of all, any questions about anything technically, logistically, anything like that? Yes, question. Yeah. Okay. What is there was a question again. Let's talk about last class. Remember, we showed the I showed the reduction that vertex cover was hard from satisfiability. 3 set. Any questions about how many people understood that basically how that reduction worked? How many people didn't and have cogent questions? How many didn't and don't have cogent questions? Okay. No one will admit to it. Okay. But again, it was a you know, I consider beautiful but seemingly amazing looking reduction that took this logic thing and produced a graph thing. And the critical thing, again, if we go back to our Bandersnatch, again, you always have to go back to the Bandersnatch and Mobility slide. That's the important thing here. So what is the whole idea of what we're trying to do? We are trying to design an algorithm for Bandersnatch, okay, which works of the form translate the input of Bandersnatch into the input of mobility in such a magical way that mobility of the y is the same as Bandersnatch of g. They're both decision problems. They're both true and false problems, okay? And what we need to be able to do is, the magic here is that the translation has to be polynomial time, but that's not really a lot of magic. You know, it's usually, we're designing the thing. It's usually pretty straightforward to show that it's polynomial. Question, what? Okay, the important thing that is going to become very important today is, what do we need to know about Bandersnatch? We need to know that Bandersnatch is one that there cannot be a fast algorithm for. It's got to be a hard problem, right? And we knew that satisfiability was, because I told you. Once I told you that, though, you saw that 3 set had to be as hard as satisfiability. Because if you could come up with a fast algorithm for 3 set, you came up with a fast algorithm for all of satisfiability. Last time I showed you vertex cover is hard. Okay? Vertex cover is as hard as satisfiability. If you could solve vertex cover quick, you could solve 3 set quick. That would mean you could solve satisfiability quick, right? Bandersnatch is any problem that we know can't be solved quick. Okay? So you can start from any of the problems that we have proven NP-complete, right? Any questions about that? That's an important thing, and that's going to be part of the magic of today. Because in theory, it doesn't matter. You can do it from any one to any other one. But in practice, it's often much easier to see this translation if you pick a problem that's very, very close to it conceptually. Any questions about it? Okay, good. But what is the basic principle here? We were going to do a translation, and the magic of that translation was that whenever mobility of y was true, Bandersnatch of g would be true. And whenever mobility of y was false, Bandersnatch of g was false. In that case, we could output mobility of y as the answer for Bandersnatch of g. Any questions about that? Now the question is, wait a second. Okay, you were giving me this proof-like thing, and I said here I had a slide that said, again, I showed you how to construct this graph here, and what I want to claim is that whenever there is, if you remember how I did this thing, I built up a graph which had some vertices corresponding to the true-false literals of a three-sat problem, and I had some vertices being triangles made out of three-sat clauses, and I had connections between equal things. And what I argued was that there was a cover of size n plus 2 times the number of clauses if and only if the original thing was satisfiable. That way, asking, does this graph have a cover of size n plus 2c, is the exact same question as saying, does the original thing satisfiable? Okay? So I have to prove that whenever this thing has a cover of the right size, there was a satisfying solution. And whenever there is not a satisfying cover of this size, okay, then the thing did not have a satisfying truth assignment. Okay? I've got to prove that whenever, again, when this says true, sat is yes. When this says false, sat is no. Okay? And the argument of how you can do that is basically by proving that if I have a cover of the right size, then it is satisfiable. And whenever I have so whenever I have a cover of the right size, it's satisfiable. Okay? Meaning that the cover, actually, to be precise, actually, my claims are, first, every cover, every satisfying assignment gives me a cover of that size, and every cover of that size gives me a satisfying truth assignment. By proving that, I've proven basically both the cases of true and false. Okay? Let me say that again because it looked like I was weaseling out of something. I prove here, basically, every time I have a satisfying truth assignment to this thing, if the thing was satisfiable, then there is a cover of this size. Okay? And I'm then going to show whenever there is a cover of this size, the thing is satisfiable. Okay? That's why I need to be able to go both ways to prove that when one says true, the other is true. When this says false, the other is false. Or equivalently, whenever this says true, that is true. And whenever this one is true, that one is true. That's why I have the two parts for this. Any questions? Yes?
So does that mean to prove that one reduces to the other, you're going to prove something harder, which is that each of them reduce to each other?
No. What I'm trying to do with this proof, let's go back to Bandersnatch and mobility, because I think what I need to have happen. And that's what I claim I am wanting to do. I am claiming that whenever I did this translation, okay, that if I look at it, I give a translation from Bandersnatch of G to mobility of Y. I need mobility of Y. If mobility of Y is true, I need Bandersnatch of G to be true, right? And if mobility of Y is false, I need Bandersnatch of G to be false. That's what it means to have the correct transformation. And I've got to prove that that's true, right? Okay? So I've got to be able to show that basically if I have an answer, if mobility of Y is true, then Bandersnatch of G is true. And if Bandersnatch of G is true, then mobility of Y is true. That's when I prove that the transformation is an exact match of the two. Any questions? Yes?
Is this how the reduction from the Hamiltonian path to the traveling salesman went?
Is this how Hamiltonian path to traveling salesman? Again, what did it go by? It was a Bandersnatch-Mobility argument. One of them, I didn't talk about this in class, I guess you're looking at this from the book, but presumably what I did there was say, if we knew that traveling salesman was hard, I gave an algorithm for solving if I knew that again, I don't remember what's in the book, because, but I think I said that if I knew that, that traveling salesman was hard, okay? Actually, wait, since I don't know what's in the book right now, I'm a little confused, I'm not sure what I'm talking about here. But again, how does this thing work? Recognize the big structure of what it's doing, okay? There are two problems, one of which you know is hard, one of which you're curious about. Does everybody see that? The reason I'm confused is I know both of those problems is hard, so I don't know what I'm trying to prove, right? Okay? But basically, the one that you're trying to prove hard is put here, and the one that you absolutely know there is no fast algorithm is Bandersnatch, right? And I am doing a transformation, and I've got to prove that, it's easy to do a translation, but the hard part that I need is the property that mobility of y always has to equal Bandersnatch of g. And you've got to prove it kind of both ways, that when this is true, that's true, and when that one's true, this is true. That's the way you prove that the problems are the same. Any questions? Yes?
If you have a problem that's easy to solve, is it ever possible to reduce it to a problem that's difficult to solve?
So suppose, let's say, that Bandersnatch was a very, very hard problem, a known hard problem, SAT, 3-SAT, one of these. And suppose mobility, you show a translation to mobility where mobility is shortest path in a graph. We know there's a fast algorithm for shortest path in a graph, right? What would happen if you came up with a translation to shortest path? You would have a fast algorithm for solving your known hard problem, right? What would that mean? Okay? One thing it would mean is that you're now famous, because nobody knows how to solve any hard problem in polynomial time. That's what it would really mean. Because the definition of hard is sign of that we can't solve it efficiently. Okay? Let me say that again, because I'm getting a blank look, and this should be kind of a punchline that is grabbed. Okay? If, by definition, Bandersnatch is a problem that we know is hard, or we think for extremely good reasons is hard, and if you did such a translation, and you did it to a mobility where there was a fast algorithm for mobility, you have just given a fast algorithm for Bandersnatch. Do you agree with that? Okay? If you're giving a fast algorithm for Bandersnatch, how could Bandersnatch be hard? Okay? And so either you've revolutionized computer science, or you've done something wrong. And, we can take bets on that. Okay? But you understand why that is happening. This reduction either gives you a fast algorithm for solving this, okay, if there's a fast algorithm for this, or if this algorithm is known to be hard, it's giving me a proof that this problem is hard. And that's the way that we expect to be using it in this section. Any questions about that? How many people understand the reasoning we're doing here? Okay? Any questions? How many people don't and have any questions about it or good? Any questions? Okay? The reasoning is, at some level it's one slide's worth of reasoning. On the other level, it seems like we're doing things kind of backwards. And so you've got to make sure that you understand what we're doing here. Any questions? Yes? Okay, well, wait, no. Let's take a look at this. Suppose Bandersnatch is a problem I don't know how to solve. right? I don't know if there's a fast algorithm or not. And suppose you show me how to solve it using a problem where, let's say, where there is no known fast algorithm for. Maybe we use, satisfiability to solve it. If mobility was satisfiability and Bandersnatch was an unknown problem, what have you done? You have shown me a slow algorithm for solving Bandersnatch. Now, it may be there is no fast algorithm, but you haven't proven to me that there's no fast algorithm. Does everybody kind of see? That's the important thing here, okay? In fact, let's now go back to my favorite tweet. Remember I had a tweet I was incredibly proud of? Read this tweet, because this is exactly the whole thing here of what we're trying to do. What does an NP-Completeness proof do? Why am I teaching it to you? It's a way to prove that a dumb algorithm that is slow isn't a slow algorithm that is dumb. Okay? Now, what is an example of something? What is an example of a dumb algorithm that is slow? Yeah? An algorithm, not a problem, first of all, right? A backtracking solution, right? These exponential backtracking, try all things. What you guys did for the bandwidth problem, right? What did you do for a bandwidth problem? I claim you came up with a dumb algorithm that is slow. Does everybody agree with that? Does everyone agree that the algorithm was slow? That shouldn't be controversial, right? Was it dumb? Well, all it basically did was try all the possibilities. So even my winner, I'll say, was, still pretty dumb, okay? Any questions? But what's the point here, okay? If the problem, I show you that bandwidth problem is an NP-complete problem, you can't hope to do better than that. Does everybody see that? So what is the NP-complete problem proof doing? If you show me a slow algorithm for a problem, okay, if there's a fast algorithm for it, your slow algorithm is dumb, right? And if I have an NP-Completeness proof for it, I know there will not be a fast algorithm for it, right? So I'm ensuring that your dumb algorithm that is slow isn't a slow algorithm that is dumb. Any questions about that? Who likes my tweet? Who understands? Any questions about this? The single thing that raises my hackles the most when I talk to previous students is they think that, oh, just because I solved the problem with backtracking means the problem is hard. Does everybody see that's wrong? Hardness is a property of the problem that says you can't solve it quickly. If I assigned you guys the task to use backtracking to solve minimum spanning tree, all of you guys I could have done that, and that would have been a perfectly fine assignment. Okay? Would the fact that you used backtracking mean that minimum spanning tree is hard? No, it means you did it in a dumb way, right? And this is basically, NP-Completeness is arguing that there is, for certain problems, no ways to do it that is in a big picture different than the dumb way to do it. All possibilities. Any questions? Okay, any other questions of these issues before we move on? Okay. So what I want to talk about, I didn't get through last class's material quite as much as we did. We showed that vertex cover was hard. And I think that when you saw that reduction, that was kind of a pretty amazing reduction. Where did that come from, my God? Okay? But once we start having more and more problems that we know are hard, that can fill our Bandersnatch slot, we will notice that picking, the right Bandersnatch makes it easier for us to prove a problem is hard. Right? You have a new problem walks in the door that you care about, okay? And you want to say, hey, this smells hard to me. How would I prove myself? How would I convince myself that this problem really is hard? Well, you would want to look at what NP-complete problems do you have that look similar, smell similar, okay, that are presumably going to be closer to the problem you care about So it's easier to do a translation. Okay, any questions? So let's take a look at an example. There is a problem we talked about, actually the first or second day of class, okay, if we remember back that far, called independent set. Independent set in a graph is the following. Given a graph, okay, we seek a subset of vertices such that there is no edge between any two of the vertices. Okay? Any questions about that? How big an independent set can we have in this graph? If we want to find a set of vertices such that there is no edge between any vertices in that subset. Okay, yeah? Would it be 2? It would be 2. Which 2 would we claim? If we pick this one, any one of these other ones in the star would count. Does everybody see that? No, I can't take this one, excuse me. But if I took this, and this, and this, I would have an independent set of size 2, and I claim there's no way to find 3 vertices, none of which have an edge between them. Does everybody agree in this graph there's no such things? When did we see this problem before? Maybe you've heard something. I think maybe it was on a homework also. But remember when I talked about the movie star scheduling problem? What was that about, if you remember? You had a movie star who had a choice of picking, was being offered lots of different jobs. And they wanted to do as many jobs as possible. But certain jobs collided with each other. Does everybody see? They overlapped with each other and you couldn't do it. And the goal was to find the largest number of jobs that they could take without anything interfering with each other, right? Why is that an independent set problem? Yeah?
Because you can imagine a graph where each node is one of the movies, and there's an edge between 2 movies if they conflict.
Does everybody see? Every vertex is going to be a movie. Every edge is going to be, there's going to be an edge between any 2 movies if they overlap in the time that they're making them, right? And our movie star wants to know what's the most projects they can take, okay, without any collisions. Does everybody see that that problem is a independent set problem? How many people see it? How many people don't see it and want to see it? Any questions? Okay, good. Now my claim is that this problem is going to be a hard problem. Okay? If this problem is going to be a hard problem, is it going to be a Bandersnatch or a Mobility? If we want to prove that this problem is hard, is it a Bandersnatch problem or a Mobility problem? Okay, we're getting confused again. That's why we always have to go back to this slide over and over again. Okay? Boom. Sorry if it's taking me so long to get back there. What is the problem? Okay, if I want to prove that maximum independent set, the movie star problem, is hard, which role is it going to be? Is the movie star problem going to play the dramatic part of Bandersnatch? Or is it going to play in the Mobility role? Who here says Bandersnatch? Who here says Mobility? Okay, so we need to do what? We know that maximum independent set, return maximum independent set on some graph with some bound. What problem should be Bandersnatch? Of all the problems we know about, which problem smells most like Bandersnatch? That is a hard problem. Yes? You say vertex cover smells like like maximum independent set. Why does it smell like maximum independent set?
Because the vertex cover tries to find things which tries to find a cover which touches every single edge, whereas maximum independent set kind of does the opposite of that, where you want vertices that don't touch any.
Okay, you're making a higher level analogy here that is necessary at this point because we're choosing from very few possibilities, right? Okay, one possibility is that it's a graph problem, right? So it looks more like the other ones because it's a graph problem. What else is true about it? It also both of them are about subsets of vertices. Do you agree with that? Okay, yeah.
By requiring the vertices to be all non-connected, it's analogous to each vertex having a color, and then picking the color of all those vertices.
You mean color or cover?
A color, and then you pick the maximum color.
Okay, you're making some connection between this and coloring, which I guess we talked about two coloring, right? Well, what happens when there is a connection between coloring a graph and an independent set? What is the maximum independent set of a bipartite graph? Remember we talked about these two bipartite graphs? These bipartite graphs that looked like bunk, 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 and all the edges went back and forth? What was the maximum independent set of a bipartite graph? Yeah, you can continue.
The larger of the two sides.
It's either going to be all of these guys or all of those guys, right? So you're saying, hey, there is a connection between coloring and independent sets. And that's good. You're seeing an analogy. This is what we're looking for, are analogies. The bad thing is, I haven't told you that coloring is hard. I told you, but didn't really prove to you that coloring is hard. So that's not where we're going to start. But you have noticed that we have one graph problem. That might just be where we start, okay? Now, what is the connection between, let's go back. So you want to say, let's come back, sorry about this. I'm sorry if I'm getting a trouble. It's funny, I'm having a problem here. Okay? Okay. You want to say that vertex cover on a graph G, is there a cover of size J? Okay? We want an algorithm that will find a vertex cover, construct a new graph and a new bound such that if this graph has an independent set of this size, this graph is going to have a vertex cover of that size. Does anybody see a way we can construct G prime and K prime such that these two things are the same? Yes?
I haven't fully fleshed it out, but G prime I think should be the graph which inverts all of the edges in G. So if there is an edge between the vertices, then delete it. If there's not, then insert it.
Okay, you want to take a complement of a graph. I can hold that thought for a little bit. But that's not what I'm going to do here. Okay? Yeah?
I think I just basically take the same graph.
You want to take the same graph G, and what is K prime going to be? What is the independent set size in this graph?
So all the vertices, suppose the number of the vertices will be n, so it will be n minus k.
Okay? What has this man done? Okay? This man has noticed that if you have an independent, a vertex cover in a graph, what happens if you delete a vertex cover in the graph? Okay, what is a vertex cover? Does anyone remember what a vertex cover is? Yeah?
Set of vertices that are adjacent to either R or are adjacent to all the vertices in the graph.
A set of vertices such that every edge kisses it, right? Kisses one of the vertices in that set. Does everybody agree with that? Now, what happens if you delete all of these vertices in the cover? Okay, all the kisses die, I guess. Recognize that. If there's an edge between me and you, if I die, there's no more edge. Does everybody agree with that? Okay? So what's going to happen in a graph if you delete all the vertices that are in the vertex cover? Yeah? It will not disconnect it. Not only will it disconnect the graph, it will maximally disconnect the graph. Every edge will die. Does everybody see that? A vertex cover, if I've got a cover, every edge is either kisses the cover once or kisses the cover twice. Does everybody see that? If these two are my cover, what's going to be left? After I delete all of the edges that touch these, everything is going to be, if there's no edges, Is it an independent set? Yes, that's the definition of an independent set, right? So does everybody see that this is the transformation that we want, actually? How am I going to give you an algorithm to solve vertex cover? If I have a maximum independent set solver, okay, I'm going to take your graph and ask myself, is there an independent set of n minus j vertices? If there is an independent set of size n minus j vertices, what does that mean? The remaining vertices touch all the edges in the graph. Does everybody see it? The remaining vertices are going to be a cover. And how many remaining vertices are there? n minus j, which is what? J. Does everybody see, and this is important, this is one you got to look at and understand, this is an algorithm for solving vertex cover, okay, quickly, if maximum independent set could be solved quickly. Okay, how many people see the transformation? Now this is something that seems to me perfectly reasonable for someone to do on a final exam, right? Is this a ghastly reduction like we had said before? No, this is a nice simple reduction, okay? And the amazing thing is that there's a lot of problems that the reduction is actually fairly simple once you start from the right place, okay? Any questions about this, what I did here? This is like what I expect to see on a homework or an exam. Yes?
Is this logic reversible?
When you say logic is reversible, what do you mean?
Can you, if you have a BC solver, can you make it a max IS solver?
So what's true is, you could, these are in fact, you could, now that you could also have written now a max IS solver using vertex cover. Does everybody agree with that? If I gave you a fast vertex cover solver, would that give you a fast IS max independent set solver? Yes. Okay, but again, for me to prove something hard, I start from one I know is hard. This one I knew was hard earlier than it. But now that I've proven this hard, if you didn't know vertex cover was hard, yes, you could have used this as Bandersnatch, and that is Bobilly, and the same basic idea would have worked. Okay? Yes?
So does this make maximum independent set in this, like a similar equivalence class? Is this difference between complete and hard that you can map them both back and forth?
No. Okay? So the question is, what is it, the difference between complete and hard? Okay? And I'm going to decide whether I want to tell you this. Okay? So to me, I usually use them as pretty much indistinguishable. Okay? So you've probably heard me, how do you know about the difference between hard and NP-complete? You've probably heard me use both these terms, right? The real dope is the following. Okay? That a problem is hard when I prove it is at least as hard as some other hard problem, right? So this proves that maximum independent set is hard. Why? Because vertex cover was hard, and this proves that maximum independent set has to be at least as hard as vertex cover. What does it mean to be NP-complete? Okay? It means that it is hard, but it is also solvable in non-deterministic polynomial time. Now, what does that mean? Okay, this is why I didn't really want to talk about it. Okay? But it really means that if I told you the answer, you could check it quickly. Okay? Suppose I give you this graph and say, here I give you the Facebook graph. And I say, find me the an independent set of size 696. You would say, oh, I can't do that. That's hard. I got to search through everything. Now, suppose someone said, here is what I tell you is an independent set of size 696. Can you prove that it's an independent set? How can you prove, if I give you a set of vertices, how can you prove that it's an independent set? Yeah?
Just by checking in the original graph.
Checking in the graph for every pair of these guys. Are these guys friends? No, 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 no. Do you see that it's sometimes easier to solve a problem if somebody gives you the answer? Okay, you're sitting at an exam. Okay, you're faced with this problem. You're sitting in the exam. You don't know the answer to something. What do? Okay? Okay. Now, how do you know that the guy is, do you trust it and write it down? Well, hopefully you shouldn't, okay? But certainly if you're going to do it, you'd better be able to check that it's true before you copy it down. Is that right? Is it easier to check this guy's answer than to come up with your own? Probably. Okay? So what do we say? We say that a problem is NP-complete if I could check the answer in polynomial time, and yet it is hard. Okay? And to cut the chase, almost, I think, everything we have talked about all semester is in NP. Okay? There are problems that are not, and this is, you take an appropriate theory of computation course, you might talk about them. But just about all the problems we have talked about in here, I think probably all of them are, in fact, in NP. So that's why I get sloppy when I say NP-complete or NP-hard, because it's usually the same thing. Yes?
So is there any use to saying that something is equivalent, or like in the same equivalency class, not at least as hard as?
So sometimes there's problems that are in NP that are not known to be hard. Okay? So one problem that is in NP that is not known to be hard is shortest path. If I gave you the answer to a shortest path problem, is there a path of 693 miles between here and California? Could you check that in polynomial time if I give you the path? You would say, yeah, I can even compute the whole thing from scratch, right? Problems that are in P, polynomial time, means we can compute it. You don't need to check it. You don't need to copy from the guy next to you, right? But there's other problems. So basically, what is the case? There's certain problems that you could check the answer for, but it's not known or whether they're hard or not hard yet. And if they're not known to be hard, then they're not hard. Yes?
What about something like chess, where like even checking an answer would take a ridiculous amount of time?
Okay, now you trapped me. I said almost everything we talked about is in NP. What is an example of something that's not in NP? What about prove to me that that there's a winning position in chess? Okay? You know the game chess, right? You could imagine a world of a chess problem where the player who's white says, "I win." Starts out the game starts, the player white would say, "I win." What do you mean? There's a provable win from playing white, okay? You know that in certain chess positions you can prove that white has a win, right? If you have two rooks and a queen and the other guy has only a king, you can pretty easily prove that you're going to win the game, right? There is an algorithmic problem of the type, given a board position, okay? Does white have a forced win from here? Is the answer to that yes or no? The answer has got to be yes or no, right? Either white has a forced win or it doesn't have a forced win. So it's a decision problem, right? Now suppose, let's say, Magnus Carlsen in the last World Championship match moved his first king out. He was playing white. He moved his pawn out and said, "I have a win. You lose. You should resign." Okay? What would the component say? Prove it to me. How would you have a short proof that you win? You could construct the entire tree of moves. Does everybody see that? You could prove to me that you have the win by saying, look, you could do all of these possibilities. And if you do this, I'm going to do that. And then for all of your possibilities, I'm going to do that. And if we go and look deep enough, look, every one of these things I do, I end up on a win. Does everybody see that? That would be a proof that I'm right, right? But I claim that this is such a big and complicated proof, you can't check it in polynomial time. And so that's kind of the difference between this NP thing and more complicated things. Okay? Yes?
Do we call it deterministic because we can predict the polynomial?
Okay, so this is why I hate talking about this. Okay? You know, I've taught you all semester, and none of you know, I've talked about a lot of things, nobody's had any curiosity. Stuff that I don't want to talk about, everyone's curious about. Okay? And I know why. Okay? But what is the difference? There is the notion of deterministic and non-deterministic has to do with whether or not it's kind of deterministic means it's like one of the algorithms we talk about. Non-deterministic is sort of like somebody is magically going to give you the answer, like the guy next to you who you're looking at, right? So the non-determinism has to do with the answer magically appearing, okay? You know, on the test next to you or something like that, okay? Any questions? Yes? On this particular problem, vertex cover and maximum independent are so closely related. The transformation is basically that it pretty much you could make it go the other way. You may have to rewrite it a little bit, okay? But what does that mean? That means these two problems are so closely related that the guts of solving one is the guts of, you know, it's like if I tell you, you know, basically it is so closely related that solving one is essentially the same as solving the other. That's really all that's happening here. Any questions? Yes?
So if we don't do the proof backwards, will we know maximum independent set is harder than the VC?
So what have we done? We have proven here that maximum independent set is at least as hard as vertex cover. Why? Maximum independent set has the power to solve vertex cover, right? So it's got to be at least as hard, okay? The truth is that in my business, they're all equally hard. That's the way that I usually think about it, okay? So I don't really get points for proving it the other way, okay? Any questions about it? Okay, yes?
Can you also show that maximum independent set is hard using the same way you showed that vertex cover is hard?
Could I have started from satisfiability, okay, and translated it into a maximum independent set starting from satisfiability? Could I have? The answer is yes. And how could I have done it? If you think about it, what if I have two programs? Before I had a program, I showed you a program that took sat and translated that into vertex cover. Does everybody see that? What if I took that and fed the output of that program into this translation? Wouldn't that do the job? This is why I say theoretically you could start from anything. That's if there's a way to prove it hard from one problem, there's a way to prove it hard from any of these other problems. But this is a messier thing because it's composing two different proofs, right? Two different translations. Okay? So picking the right problem to start from is a matter of convenience, not a matter of fundamental, you know, these things are the same, right? Any questions? You know, you can make it easy or you can make it hard, okay? You make it difficult for yourself or not. Okay, you pick from the right problem, it's easy. Pick from the wrong problem, it's difficult. Yes? Can I prove that that I can do it from any other NP-complete problem to any other problem? The answer is yes. Okay? What would be my proof? If you think about what I've been doing here, okay, we started from SAT, which was the mother of all NP-complete problems, right? I showed you a way to do that to go build 3SAT, right? And from 3SAT, I showed you a way to do, what was it? I used vertex cover. And from vertex cover, I showed you a way to do independent set. Does everybody see this? Now, is there a way to do it from SAT? Okay. It should be clear that following these chain of proofs is enough to show you that I could have used anything on this starting point. by just composing the proofs. That's what she was asking, right? You're asking, wait a second. Later on, if I give you enough time, I'm going to show you another, actually from 3-SAT, for example. I'm going to prove, if I have enough time, that subset sum is hard, right? Could I show that there's a transformation between subset sum and independent set or something like that? That you're skeptical of. Turns out that there is a famous, powerful theorem called, called Cook's theorem. That is, so you can look this up if you need something to Google. Google Cook's theorem. That basically shows all of these problems have a reduction back to set. Okay? And that then gives you a move between any pair of these problems, right? You could either go down, or you could go back up to set and then go down. Does everybody see that? From here, I could go back, follow Cook's theorem to go back up there, and then go back down to there. Okay? Any questions? Okay? Okay. Let's step out. Any other questions quickly about what this stuff means? Okay, yes?
That just means it's possible, not that it's the best, though, right?
That means that it's possible. That means it's a grungy way to do it, right? If you think about what we're doing here, we're talking about these transformations are like compilers translating from one to another. Is that right? Do you ever want to look at assembly language after it's been translated? It's messy. It's ugly, right? Okay? So yes, following the chain of these transformations is complicated, right? But the amazing thing is that there are these links of transformations. And once you understand it, at a reasonable level, you see why that is. This Cook's theorem proof is not something I'm going to wouldn't do in here, but if you're a smart student and you're really excited, you could understand this. Okay? Any questions? Okay? Okay. Any other questions about what this stuff means? Because I don't want you to worry about what it means. Yes?
The way that you prove something is hard is by using another problem that's hard?
The way that you prove that a problem is hard is you say that the way I prove a problem is hard is it plays the role of mobility. Okay? I find me a Bandersnatch, and I show you how to translate that Bandersnatch into the mobility. And if there was a fast algorithm then, after that, if there was a fast algorithm for mobility, that would give you a fast algorithm for this hard problem. Okay? If it's hard, that means there is no fast algorithm for it. If you're going to tell me that something magic happens, if this is true, what does it mean? It's not true, right? If there was a fast algorithm, if a fast algorithm for this gave me a fast algorithm for something that doesn't have a fast algorithm, this thing cannot have a fast algorithm. That is how we prove things hard. Any questions? Yes?
But then, how do you show, is there a very first hard problem?
The first hard problem is satisfiability. And why is it the first hard problem? Because I tell you it's a hard problem. Okay, is one reason. Because every algorithms person in the world knows that if I could come up with a fast algorithm for satisfiability, I would get $1 million and I'd be famous. And other reasons, like this magic Cook's theorem that shows that all these problems translate to satisfiability. Meaning, in fact, if I could come up with a fast algorithm for satisfiability, I come up with a fast algorithm for everything under the sun. Okay? And all these things are impossible to believe. That's why satisfiability is hard. Yes?
Is there a way to prove that a fast solution to a problem doesn't exist without assuming that a fast solution to another problem doesn't exist?
So you're telling me, is there another way to prove things that are hard? The answer is not in a, let's say to a first approximation at least, let's say no. So there's no useful tool that people would use to prove problems are hard. There may be some artificial ways, for certain artificial things that are very restricted. This is the way that we prove problems hard. I am extremely comfortable assuming satisfiability is hard. I do not lie awake at night saying, oh, what if I've been wrong? There are great reasons to believe that satisfiability is hard, okay? And any of those ones that I've given you should be enough to convince you, okay? And this is one I sleep very comfortably at night saying that. Any questions? Okay, yes, last one.
So you can use this technique as with any class of problems, right? Like if you use a sort as Bandersnatch, and you have another problem that you can reduce it to, then you prove that problem has to take at least n log n time.
So what you're saying here, and again, if we jump to the very end of, I don't think it may even be at the end of these slides if you really care about it. We're not going to get to it. What is this? Is this going to go down? Boom, boom, boom. Oh, no. On the slides I'd meant to do today, okay? If you go to the end of those slides, you would see that I do give you a way to prove. This idea of a translation, a reduction between problems is a powerful idea, okay? If you do have a fast algorithm for this, that does give a fast algorithm for that, right? And so sometimes the best way to find a fast algorithm for this, if it's not NP-complete, is to do a reduction to an algorithm problem you do have a fast algorithm for. If you have a fast algorithm to sort, okay, and you can show that you can solve your problem by sorting, that's good. And if you have an algorithm problem like sorting, which we know takes n log n time, and if you can give me a transformation to some other problem, this problem also has to take n log n time. I do that with convex hull in the notes, which I'm never going to get to this week. Any questions? Okay, let's go back and remember where we were, because these are good digressions, but they're a little bit of a digression. Okay? Does everybody agree that vertex cover is hard, right? And that independent set is hard? Any questions about it? Again, recognize, again, with all this question, what is NP? What does it mean? How hard is satisfiability? These get technical issues and are complicated. The amazing thing is that to prove that, give you a good reason to believe that something is hard can be amazingly simple to show. It's one of these lousy reductions. Let's look at another one. What is the problem of a clique in a graph? Finding a clique in a graph is finding what is, we say a clique is a subset of vertices such that every pair of vertices is connected. Does everybody understand that? Okay. What is a clique in friends in high school? When I was in high school, people worried about cliques. Do they worry about cliques these days in high schools? Maybe they're posses. What are they called these days? Okay. What is it? It's a group of friends who hang out together, right? And every one of them knows everybody else. Does everybody kind of think about it? So if you have one of these gangs or posses or whatever you call them these days, on Facebook, what's the case? Every pair of them are friends of each other, right? What if we wanted to find in the Facebook graph, what is the largest posse, okay, or clique, or whatever? I call them a clique, okay? A clique is a subset of vertices such that every pair is connected, okay? What is the size of the largest clique in this graph? How many vertices are in the largest clique in this graph? Look at this. Where's the largest set of vertices that every pair is a friend? Yeah? 5, right? The star, the satanic symbol here, right? Does everybody see that? Okay. Any questions? Okay. So what is the maximum clique problem? I give you a graph G and I give you a graph K, J, and I ask, is there a clique of size J or larger? Okay. How would we prove this problem is hard? Any question about what the clique problem is? Is this going to be Bandersnatch or Bobilli? If we want to prove clique is hard, is this going to be Bandersnatch or Bobilli? Bobilli. So what do we want to do? We want to find an algorithm for solving clique on what? A graph G prime Let's call it K prime. Again, I like those letters. We know we want to describe in our transformation how do you construct G prime and how do you construct K prime. And we need a Bandersnatch problem. What Bandersnatch problem do we have that smells most like clique problem? Okay, yes? Maximum independent set. Why do you think maximum independent set smells like the clique problem?
In that graph, at least, the maximum independent set was size 2, and the size of the maximum clique is the number of nodes minus the size of the maximum independent set.
Okay? You want to claim that, let's think about it. What you want to claim here is that you want to claim that the maximum, you want to use maximum independent set here. Is this what you said? Or did you say vertex cover? Which did you say? Maximum independent set here. And so what is your transformation going to be? Okay? Your claim is going to be that G prime is going to be what? Oh, this thing had a G and a K, let's say, as an arguments, right? So what is your reduction going to be? Same graph. And what's K prime what's this going to be? N minus K. Okay. Is this the transformation that we want? Is it the case that if we take a clique, okay, and we delete it, we get an independent set? Not necessarily, okay? You're saying in this particular example it looks like it works, right? Can anyone give me a graph where this is not going to work? Okay. I don't think it's going to work yet. What? See, that's sort of the tip-off here. My independent set was this and this. Does everybody see that? And it was not these two. That's the tip-off why this isn't I don't think that your transformation is right. Can anyone give me a graph where what he's saying isn't true? Okay, yeah? Okay, what you're, I think, saying is, what if I had taken this graph? Maybe let's see if this is what we agree on. This was the graph that you had here. What if I add another vertex connected to these other two, right? You see what I'm doing now? Now, what is the size of my original graph was n. N is equal to 5 is equal to 8. My clique size, K, is equal to, 5. What is the largest independent set in this graph? Does everybody see that it's still 2? Okay, do you agree with this? You can't see it. Okay, let's try it again on a bigger part of the board. Does everybody see that if I add, let's say I take this thing here. Actually, I hate to do this, but let's try this. What if I now add a vertex here? Hello, hello, am I back? Okay, good. Okay, what is the case here? Sorry about that. Do you see that on this particular graph now, n is equal to 9, n is equal to 8, the size of my clique k is 5. What is the size of the largest independent set that I can have? 2. Does everybody see that I can pick one of these and one of these, but I can't pick more than one of any types? Does everybody see that? I've got a clique here of size 3. My independent set can only have one of those vertices. I've got a clique here of size 3. I can only have one of these vertices. Does everybody see here that my independent set, which I think you're calling K prime, should be equal to 2? And so your relationship doesn't hold. Do you kind of agree with that? Yeah. Okay. So this is informative. This is an example that these reductions are not just strings of symbols you write down on the page, right? You've got to kind of show that you're translating the problem in an appropriate way, that it preserves what makes it right, what makes the thing the same, right? And so what you're kind of saying is we would like to have this clique kind of be the independent set if you're doing the translation. That's kind of the thing you're thinking about, right? How can we do that? Yes? Is this where you'd want to complement the graph? How do you complement the graph? Say, nice graph, right? Okay. Actually, what's the other way to do it? What does complementing a graph really mean? Okay. Yeah, anyone remember? Yeah?
Delete edges where they are and add edges where they're
Replace edges with what they actually, whenever there was an edge, take it out. Okay, when there is an edge, replace it. Does everybody see it? What happens when you complement the graph? What's going to happen when I complement this graph? Okay, here I'll try to draw it again. Those 5 vertices, what's going to be the complement of that clique? You have it, right? Everything that was an edge is gone, right? For this thing had an edge, it's gone. What do I know? If I complement it, what's this thing going to be adjacent to? Well, it's going to be adjacent to everything except this and this, because it was adjacent to this and this, right? So, shoom, 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 shoom. Does everybody see this? Delete the top edge. Right. Does everybody see that? Okay. Now, what is interesting if I complement the graph? Does everybody see that what used to be a clique is now an independent set? And what used to be an independent set is now a clique. So what is the right transformation here? What if I say G prime is the complement of G, right? And what's K prime? What's the size of the independent set I'm looking for? Okay, what's the size of the clique that I'm looking for in this graph if I want to find an independent set? Okay, let's say that again, because this is the punchline. Look at this enough to see if you can guess the punchline. Okay, I want to find the clique in graph G prime. Okay, of size K prime, such that this will have a clique of size K prime, if and only if G has a clique of size K. So, what is K prime going to be equal to? Yeah? K. Does everybody see this is the transformation that I want? Right? Whenever I'm going to take the graph and complement it. Now, what was a clique becomes an independent, what was an independent set becomes a clique. And that's very convenient because I have a fast clique solver here, right? If I have a good clique solver, If you complement the graph, whenever you find a clique, you found an independent set. If you found the largest clique, you found the largest independent set. But what's the problem? There's no way to find a fast independent set quickly. So therefore, there's no fast way to find a clique quickly. Any questions about that? Yes?
Is it a coincidence that that graph became bipartite after we complemented it?
Is it a coincidence that this was bipartite? The answer is yes. Every bit as much of a coincidence as the fact that those numbers worked out the way he wanted them to work out. Okay? Yes?
Doesn't it become partite in the number of clicks in the original graph?
What is true is the following. Suppose, let's say, your graph consisted of, was covered by a certain number of cliques. What is a covered by cliques? Suppose you could take your graph and break them into, let's say that you partition the vertices into a way such that each part is a clique. Okay? Then if I complement that graph, do we agree that there's no vertices, edges between things in this part? By definition, if this is a clique on 3 vertices, if I complement it, there's going to be no vertices here. Does everybody see that? And so there is a relationship that if you can partition the vertices into, and there's also maybe other edges, but if you can partition the vertices into k cliques, then if you take the complement, it is a k-partite graph. Okay, but that may be more complicated than what you wanted to hear. Any questions? Okay? Any questions about this about how this reduction worked? Okay? Yes?
So the idea is that overall, to solve the clique problem, we change the input set in that max independent set on the change.
Right, so how did this reduction do? To solve maximum independent set, which was the one I knew was hard, I did what? Okay, I constructed a new graph and a new bound, and I called the clique solver. And this graph G prime is going to have a clique if and only if the original graph had an independent set. Right? Because there's a complement relationship between it. Complementing this graph, the clique would give me an independent set. Okay, so I'm proving that I'm finding the same thing. That's kind of what I'm doing here. Is showing that finding this in this is the same thing as finding this in this. Any questions? Okay, let's get to the daily problem. Okay, I know I'm a little bit behind today, but I think this has been good. Okay, let's go back to the daily problem. How do I view full screen mode? Bang. What is the problem of the day? The problem of the day asks for what is the densest subgraph in a graph. What is a graph? What is a densest subgraph problem? It takes as input a graph G and integers k and j, k and y, and asks, does G contain a subgraph of exactly k vertices that has at least y edges? Okay, to kind of get what that problem is there some region in this graph that has a relatively small number of vertices, okay, k, and a relatively large number of edges, y? Okay? Any questions about what the problem is? Okay? How would you give me a way of doing it? Yes? So wait a second. If I want you to prove this hard, what is this problem going to be? Is densest subgraph going to be Bandersnatch or Mobility? Which one is densest subgraph going to be? Mobility. So do I have, if I have a subroutine for solving densest subgraph, what is the input to densest subgraph? It looks like it's a graph G prime. I like to call them primes just down here just to make it easier for me. K prime and Y. Let's make it Y prime. What are you going to use? We need a Bandersnatch. What Bandersnatch are you going to use? Clique. Clique had as arguments what? Is there, in a graph G, is there a clique of size K? Does everybody see that? Now, what do I need to do? I need to now specify how do I construct G prime, K prime, and Y prime such that I can call my densest subgraph solver. Does everybody see that's what I'm trying to do? Now, let's complete the idea. What is my transformation?
So G is the same, K is the same, Y is equal to K times K minus 1 over 2, which is the number of edges that we would have.
Okay, so what's she saying? She's saying, what if I feed a densest subgraph solver? I give it, ask, do you have a set of K vertices which have between them K choose 2 edges? That's basically what she was saying, right? K choose 2 means all pairs, right? How many edges are there in a clique on K vertices? How many edges would there be? Well, let's take, how many edges are on a clique of size 1? How many edges? 0, right? What was K choose 2? Just let's get back to this. That's K times K plus 1 over 2. Does everybody see that? Okay. These are the number of pairings, right? Do we agree that asking, is there a subset of K vertices with at least K choose 2 edges? Is that the same thing as asking, is there a subset of K vertices such that all pairs are created or connected? Okay, this is when I want to see some vigorous head shaking, okay? Think about it. Is asking the question, does there exist K vertices in this graph which have at least K choose 2 edges between them? Is that the same thing as asking, is there a clique of size K in this graph? Yeah?
Are you worried they're going to be connected to the wrong places or something?
I'm not worried about anything, okay? I think this is right, okay? But I want you to make sure you understand. This is the kind of thing that can be asked on an exam, right? Or a homework or something like this. So this is one I want to make sure people understand, that this kind of a reduction. Why is this the same thing? Okay? Well, what is a clique? A clique is a set of K vertices where every one is connected to every other one. Does everybody see that? That means that each of the K vertices is connected to all of its K minus 1 other neighbors. Does everybody see that? And because each of these edges count as a, and because we'd be counting each edge twice, a clique on K vertices contains exactly K choose 2 edges. Does everybody see that? So if I gave you a subroutine that, given a graph, could tell me for any K and Y, is there a subset of K vertices such that it has at least Y edges, okay, within it? Does everybody see that if you set Y equal to K choose 2, you're really asking, is there a clique of size K? That's the logic that we're doing here. How many people see that logic? Okay? And that is why this is the transformation. Because if there is a clique, a set of, the graphs are the same. If you show me K vertices with K choose 2 edges in it, I'll show you a clique. Does everybody see that? And if you show me a clique, I'll show you a subset of k vertices, which have k choose 2 edges on them. They're the same thing. So finding the densest subgraph has to be at least as hard as finding a clique. And finding a clique has to be at least as hard as maximum independent set, which has to be at least as hard as vertex cover, which has to be at least as hard as 3-set, which has to be at least as hard as satisfiability. And we know what about satisfiability? It's the mother of all hard problems. Any questions about this? These are the kind of reductions that I want you to be able to do. Okay? Question, yes?
G prime, someone said that using the same graph. So is it G prime or G?
So we're using the same graph. Okay, so what I'm doing is I am trying to write a program that is easier to document. Okay, if you think about it, let's think what we're doing here. This is an algorithm that is designed to pass arguments to a densest subgraph solver, right? That's really what it's doing. Now, in fact, I could have passed G directly. Does everybody see that? Okay? But as far as how do I sketch these things out structurally so I know I'm doing a reasonable thing, I first specify I know where my Bobilly goes. I know I need to have a Bandersnatch. I know I need to have arguments to my Bobilly. I need to describe in my transformation exactly how did I get those arguments. And so this is why I like to write it this way. Okay, sometimes you're able to copy the exact same argument, especially in a very simple reduction. Okay? But structurally, I like to make sure I have the right structure to what I'm doing. And does everybody see the right why my structure works this way? Yes? Oh, is this all you want me to do? If that's all you want me to do, that's fine. Then no speed. But you see how I have a nicely well-formatted NP-Completeness proof? That's what I like, is a well-formatted proof. Any questions? Let's think for another minute. I have 2 minutes till I send you out. So yes. Are you now allowed to use, actually wait, in fact now I'm definitely going to use the next 2 minutes. Don't anybody move. Pass these things back very fast. Very fast. Pass them back. Nobody leaves the room. Okay, very fast. Okay? Okay, I'll tell you what it is after you pass it back. But what is my saying here? So the question is going to be, are you allowed to use densest subgraph as your Bandersnatch? That's really what you're saying, right? The answer is yes. But as I will show you in the next class, I will say it's not really a good idea. Okay? That next class, I'm going to show you how I prove things hard. And I have what I promise every year as the NP-Completeness Challenge. I'm going to have you guys pick now you understand the basic principles of how this thing works. If you look at my slides for next class, okay, I will show you my strategies for proving things. And one hint I'll give you is, generally speaking, I like to start from a very small number of different possible Bandersnatches. Okay? So clique is one of my favorite Bandersnatches. 3-sat is one of my favorite Bandersnatches. This Bandersnatch is not one. Okay? Why isn't it? Well, this problem is pretty close to this, but it's a little more complicated. You see how it's got